Okay. So as I was saying, let's plan to make the first midterm on 22nd of March. So we have 2 weeks. So that means I should start immediately posting all the stuff on Meteo Online. So there's no course videos or lecture notes there yet, but I should start putting them. Okay, but again, the final announcement will be made through Meteo Online. So keep checking Meteo Online to see the latest news about the course. Okay, so let me just start with a quick review of our Tuesday's lecture. On Tuesday, I started with an explanation of how pitot tube works. So there I talked about static pressure and dynamic pressure. So if you have a flowing air, then a surface that is perpendicular to the direction of the flow will experience more pressure force, and this is used to measure the speed of the flow. And so I defined free stream here, and you need to be careful when placing your pitot tube so that you can get a better measurement of the free stream velocity. Otherwise, the velocity around the surface of the aircraft will be changing, and you don't want to know that. You want to know the actual free stream velocity of the air. And then I defined some terms related to an airfoil. I talked about the camber and thickness of an airfoil. Let's go down, and what else? Okay, so this was probably one of the most important topics of our previous lecture, which is the angle of attack. It has a very simple definition, and whenever you want to know the angle of attack, just remember the definition, okay? And if you do that, there's really nothing difficult about that. But on certain cases, it may be difficult to see. So that's why you should always remember the definition. If you do that, it will be easier for you to understand where the angle of attack should be. Okay, so and I showed you these pictures, which represent the pressure variations around an airfoil. So these are more realistic representations of pressure around an airfoil. Without the flow, you have the same pressure, but when there's a flowing air, then the pressure will be changing. On the lower surface, the pressure will be slightly increased, and on the upper surface, it will be decreased. And then I showed you the difference between the two, and I finally showed you this red distribution. So this may be confusing, and let me explain why. Normally, pressure is a positive quantity. Okay, so when you have a gas, it can only apply a force to a surface, and this force should be perpendicular to the surface. So in other words, the forces should be as shown here. So the forces should be acting on the surface. But if you look at this red one, you see this arrow shows as if there's a negative pressure. But that's not really the case, and let me explain why this is used. If you want to measure these forces, you use a wind tunnel. Okay, you put a model into the tunnel, and you turn the tunnel on. There will be a flow around your airfoil, and you can measure these pressures. And typically, manometers are used to measure the pressure. So let me see. Okay, so a manometer is a device like this. Okay, it has two openings. One part is open to the atmosphere, and the other part is attached to that point where you want to measure the pressure. So when you turn the tunnel on, there will be a pressure difference. But since the other side of the manometer is open to the atmosphere, with this device you measure the relative pressure. You measure the pressure with respect to the atmospheric pressure without any flow. That's why you measure the difference. And if you do that, you get these red arrows. Okay, so again, you don't measure the absolute pressure shown with this green distribution. Instead, you measure the difference between this and the pressure in the room where the wind tunnel is placed, and that actually gives you these red values. And typically, this is what is used to represent pressure distribution on an airfoil. So if you see any book or any scientific document about airfoil pressure, you will most probably see a distribution like this, and that's why you see these arrows, which normally doesn't make sense, but since they represent the difference, it makes sense. Okay, so let me scroll down. Okay, and then I told you that actually the aerodynamic forces are distributed. So you, instead of having a single force concentrated on a single point, you have forces acting everywhere around your airfoil. But instead of using that distributed force, we calculate the resultant of the force. We take the integral over the airfoil surface, and that gives us a single force vector. And we can use that force vector as shown here. So this is our resultant force vector, this R vector. So that vector is composed of three scalar quantities. Two of them are coming from its projections on an axis system. So you have two components that make up that two-dimensional vector, and the point where that force vector acts is important as well. That is called the center of pressure. Let's go down. Okay, then I talked about symmetric airfoils and cambered airfoils. If you have a symmetric airfoil and if your angle of attack is 0, everything will be symmetric and there will be no force in the vertical axis. That means there will be no lift force. All the aerodynamic force will be drag force. And if you place a symmetric airfoil with some non-zero angle of attack, there will be a lift force. And that is because even though your airfoil is symmetric, if you place it with an angle, it will be causing the airflow to deflect. And that change in the direction of the airflow will create a force on your airfoil, and that force forms the lift force. And then I talked about cambered airfoils, and the last thing I said was that even though on a symmetric airfoil the center of pressure is more or less a constant point on the airfoil, that's not the case for a cambered airfoil. So I think this was okay. So for a symmetric airfoil, if you change the angle of attack, the lift force changes, drag force changes as well, but the center of pressure stays more or less constant at the quarter chord point. So for pretty much all angles of attack, the center of pressure is close to the quarter chord point. Whereas for a cambered airfoil, that's not the case. You have at low angles, the center of pressure is at the back, and it may be even outside the airfoil. And if you increase the angle of attack, the center of pressure keeps moving forward, and in the limit it approaches the quarter chord point only at high angles of attack. But for low angles, it's somewhere behind the quarter chord point. Okay, so this is where we stopped on Tuesday. So that's where I'm starting today. So we are talking about a force vector, an aerodynamic force vector with lift and drag components, and this force vector is acting on a certain point, center of pressure point. So let me read from here. It is difficult to work with a force with a changing center of application. So that means while your aircraft is flying, this force vector is moving. So you take off, you start climbing, and your center of pressure is somewhere. And then you come to your cruising altitude, and then you start horizontal flight. Your center of pressure will be somewhere else. And during the flight, while turning or while making other maneuvers, this center of pressure will be moving back and forth. Okay? And for various purposes, we want to know the forces that includes center of pressure as well. So we need to know where the center of pressure is acting. Otherwise, just lift and drag information without center of pressure doesn't give the entire forces. So, to that end, instead of tracking the location of center of pressure, we can do this. We take this vector and move it to a fixed point. Okay, so for example, move it here, and assume that it doesn't move anymore. But it does in reality. So for this assumption to work, we need to introduce a pitching moment such that the actual forces acting on the aircraft are still correctly represented. So this is a very simple concept and very basic concept explained in the statics course. But since the first year students haven't taken the statics course, it may be a little bit confusing. I hope not, but I will try to explain it. Okay, so this is what we have, right? We have a force vector, and this is my leading edge point, which is a fixed point. It doesn't keep moving around throughout the flight. And as you see here, there's a moment arm, right? So this force vector will be creating a moment with respect to the leading edge, and that moment will be given by the magnitude of this force times the moment arm, and the moment arm is this L distance here. Ben çok kötü bir şey yapmışım. Kalemi odada unuttum herhalde. Hey, telefon kalem çalışıyor, güzel. Okay, so the moment due to this vector created at the leading edge is represented by this MLE, and that will be given by, this is equal to the moment arm times the magnitude of the force vector R. Okay, so in the original case, there's this single force vector, which creates a moment with respect to the leading edge. And what I'm saying here is, instead of using this R vector, I can move this to the leading edge point, but for the two configurations to be exactly equal, I need to put a moment here. And this moment should be the moment of this vector with respect to the leading edge point, which is L times R. So in other words, the force representation on the left is exactly equal to the force representation on the right. On the left, there is just a single force applied at the center of pressure, and on the right, I have the same force applied at the leading edge plus a moment given by L times R. Okay? So is this clear? It's very reasonable to do that, right? Again, if you have taken the statics course, this should be obvious, but yes. Well, that will be obvious when I talk about aerodynamic coefficients. I'm planning to start today, and next Tuesday I will be explaining that. It will be obvious at that point. But right now, just this is something we can do, right? This doesn't change anything. So it's important for you to understand that there's no difference in using either one of these two representations. And again, I will explain why we do something like that later on. Okay, so I don't know, maybe this explanation was not even necessary, but in the previous years, students had trouble understanding the equality of these two representations. That's why I wanted to explain that in detail. Okay, so let's think about what this new representation means. If you use this one, throughout the flight, this force will be moving back and forth. But if you use this representation, this force will not be moving anymore. It's always fixed at a certain point, which is the leading edge in this case. And instead of that, this force, this moment will be changing throughout the flight, right? So during climb or cruise or while making some maneuvers, the actual movement of the center of pressure is now represented by this moment term. Okay? So I explain all of this in detail if you read through this text here. So that explains what I just told you. Okay, now this is again another summary of everything, so maybe I can just pass this quickly. So what I'm saying is, so in reality there's force everywhere, but instead we ignore the forces on the other parts and we concentrate on the wing only and the tail as well, which is really not any different. It's also a wing with an airfoil. So we study the wing, which is normally acted upon by aerodynamic forces at every point. So this is the actual force situation. So we, instead of using that, we use this representation where the distributed force is now replaced by a single vector. And now what I'm saying is, instead of this, we make a further change and use this configuration where the lift and drag forces are acted on the fixed point, and we have a moment added to that. Okay, so this doesn't have to be the leading edge. It can be another point, like the quarter point or some other point on the airplane, but it is a fixed point. That's the whole purpose of doing that. Good. Are there any questions? Okay, now I will start talking about the aerodynamic coefficients, so which is another very important concept in aerodynamics and flight mechanics. So when you speak to an aerospace engineer, unless he is working with flight mechanics, he may not be able to explain what the aerodynamic coefficients are. So hopefully at the end of our next 3 hours of lecture, you will have a very clear understanding of what aerodynamic coefficients are and why do we use them, how do we get them. So all of these such questions will be answered. Okay, so before reading all the fine text here, let me start by explaining why we introduced them. Okay, so for different reasons, we want to know the forces on an aircraft, right? And that means a lot of parameters are, these forces depend on a lot of parameters. First, it depends on the flight condition, okay? So it depends on certainly the speed of the flight. And it depends on the altitude, for example. If you are flying at sea level, there will be some force. If you are flying at a different altitude, the forces will be different. It depends on, I don't know, things like temperature or atmospheric conditions, in other words. It obviously depends on your aircraft type, right? The design of the aircraft is important. Your wing design, your airfoil design, fuselage design, everything will be contributing to the aerodynamic forces. It depends on little things that may change during flight. For example, if the landing gears are down, there will be a force due to that. But if you retract the landing gears, forces will change. And we want to know that too. The pilot has controls over the aerodynamic surfaces, like elevator, rudder, aileron. As the pilot changes all those things, forces will obviously be changing, and we want to know them too. So in other words, we are looking for some mathematical equations, mathematical formulas, that will tell us what the forces are for all these possible conditions. Okay? So that's what we are after. So if for example, if I want to know the forces on this aircraft at this particular instant, I will be using these equations. And if something changes, if, for example, pilot changes the rudder deflection or, I don't know, flap deflection, force will be changing. And I'm looking for equations that will be able to tell me the actual forces, aerodynamic forces, in all possible conditions. Okay, let's see. So let's think about the lift force to start with. So I'm looking for an equation, and this equation will give me the amount of the lift force in any configuration and any flight condition I can imagine. So the aircraft type will obviously be a factor. So this lift force, if I'm working on, I don't know, Airbus A380 aircraft, it should give me the lift force for that particular aircraft. Or if I study a different type of aircraft, still whatever equation I have should give me the lift force for that aircraft as well. So aircraft type should be included in this equation. Obviously, the size of the aircraft should be included in the equation. This letter is rho. It's a Greek letter, and that is used for air density, which is obviously a factor. If the density is lower, there will be less aerodynamic force. The free stream velocity, V infinity, angle of attack, viscosity and compressibility. I will be talking about these factors, and they represent flight conditions basically. If you are flying slowly or fast, your V infinity will be changing, but other than that, some properties of the air will be changing in addition to the direct effect of the speed. So everything should be in these equations, right? And I forgot to mention them here, so let me just add that. Pilot controls or control surface deflection should be included as well. Let me edit here. Oops, I ran out of space. So this is what I like about using this computer. So I can just do that. I can make up more space for myself. Control surface deflection and so on. Okay. So hopefully you appreciate the difficulty of doing that, right? You'll have such an equation. Every single detail that has an effect on the aerodynamic forces should somehow be represented in this equation. For example, if a structural change occurs during flight, such as suppose that something happens and the tip of the wing gets damaged during flight. A bird hits it or somehow it just breaks. So even that will change obviously the forces. And having an equation that will give us all these factors is what we are looking for. Okay, so look at all these factors here. You can even add more stuff to that. So what we do is, some of the effects of some of these arguments are easy to predict, and you can have analytical equations for that. For example, the air density is one of them. Air density has a direct effect on the forces. If the density is doubled, all the pressure forces will be doubled, because density doubled means the number of molecules will be twice as much as the previous case. That means all the forces will be doubled. So you can just take it, we know its effect, so we can just take it out of these parentheses and put it here. So the rho will be appearing by itself. That means there's a linear dependence of the lift force on the air density. So now what I have is air density times this unknown function, which includes the remaining factors here. So if you look at this equation, if the density value changes with a scalar, the lift force will be changed by the same scalar, right? So if I put rho over 2, then lift force will be lift over 2. So that's what linear relation means. Okay, so that was easy enough. So the next thing is the speed of the free stream flow. So I said several times already in this course that the forces depend on the square of the flow speed. Okay, so this is a known fact. So that can be taken outside the equation as a square term, v squared. So that was easy as well. And a factor 1 over 2 is included here, so that we have 1 over 2 rho v squared. So students keep asking, where did this 1 over 2 come from? I don't really have a nice answer to that. But this 1 over 2 rho v squared is called dynamic pressure. And it is sort of like the kinetic energy of fluid particles. You know the kinetic energy expression, right? 1 over 2 mv squared. So that's for rigid bodies. But if you have a flow, the kinetic energy of the flow is represented using this term, 1 over 2 rho v squared. So if you know where the 1 over 2 term in the kinetic energy expression comes from, then this 1 over 2 comes from the same place. But I don't know where they both come from. So anyway, this is now taken outside the equation. And wing surface area is also taken outside of this function because its effect is also direct and predictable. So its effect is linear. So if I take this aircraft and just scale the wings, increase the wing area by a factor of 2, the force will be increased by the same factor. So that's also predictable and can be taken outside the function. So you see what I'm doing here? I know that the forces depend on a lot of different factors, and first I put all of them into a function, an unknown function, and I said my function should include the effect of all these arguments, and now I'm taking them out one by one, the easy ones. Okay, so what is left here is these are not really that easy to model. So the aircraft type, it includes every single detail regarding the design of the aircraft. So I cannot possibly have an equation that will give the effect of the aircraft design. So that's an unknown function for me, and it should stay in that within this unknown function. Angle of attack is likewise. I know that if I increase the angle of attack, the forces increase, but this is only true up to a certain level. As we discussed on Tuesday, the forces keep increasing up to a level, but after a while, it starts decreasing again. So that's a complicated and a nonlinear relation. So I cannot simply. So what I'm saying is I cannot take this alpha and put it outside the equation as a multiplying term. That will not give me the correct forces. So that should stay within that the parentheses of complicated arguments, let me say. And the other things, the compressibility and viscosity effects, which I will be talking about later on. So let me put these. I should really keep them there. Control surface deflections, these are obviously important. Okay, so at this point I cannot do anything better than that. So this is my equation. Lift force is equal to 1 over 2 times rho times v squared times s times some unknown function of all these things. And this unknown function that includes the effect of every single detail that can possibly affect the control, the aerodynamic forces are left within this function. And I call this function CL, and this is called the lift coefficient. So this is an aerodynamic coefficient. So in other words, aerodynamic coefficients are nothing but some functions of all the things that affect the aerodynamic forces that are not easy to model. So all difficulty is in that aerodynamic coefficient now. Okay? So let me come back to my question here. If I want to know the lift force on this particular aircraft, on this particular flight condition, what I need to do is I need to find these parameters first. I need to know the air density, which I can measure. I need to know the speed of the flight. I can measure that as well. I need to know the wing surface area. I can also know that. This is just the area of the wing surface here. Then I need to know the lift coefficient for this particular condition. The lift coefficient for this aircraft that is valid at this particular angle of attack, that altitude, for this aircraft, for this flap configurations, I can tell that the flaps are extended a little bit. Okay, so that's what aerodynamic coefficients are really. Şimdi size bir şeyler çizeyim dedim ama vazgeçtim. And the same thing is applied for all the forces and moments. So lift force is just one of them. So we have three axes, x, y, z axis. So there should be three aerodynamic force components. I know that the other component is called the drag force, and we never talked about this so far. This is the side force. It's in the span-wise direction. And there are moments. So this is the pitching moment. So this is the moment I explained at the beginning. So this is the moment with respect to the fixed point on your aircraft. And then there are moments on the other three axes as well, the rolling moment and yawing moment. So each one of these forces and moments are affected by the same arguments. So they can be, so we define aerodynamic coefficients for each one of these force and moment terms. Okay? So the lift equation becomes this: 1 over 2 rho v squared times s times CL. And this is the coefficient. And now you know that this CL is not just a simple number. It includes the effects of everything besides these terms here. So it is a very complex function, and that for every aircraft, for every flight condition, you need to know the value of that. Only then you can know the actual lift force acting on the aircraft. Okay? So this 1 over 2 rho v squared term, as I said before, is called dynamic pressure, and it's usually denoted with letter Q. So Q sub infinity means the dynamic pressure for the free stream flow. So the lift equation is Q infinity times S times CL. The drag coefficient is Q infinity times S times CD. And the side force is Q times S times CY. Okay. Now all the challenge is now, the difficulty is in knowing the values of these aerodynamic coefficients. Okay. So one thing nice about this presentation is, in fact, that's the reason why this S is included. So normally, anyway, this is dynamic pressure. So it is, in fact, a pressure term. So it has the physical units of a pressure, which is force per area. And S is an area. So Q infinity times S has the physical units of force. Okay? So on the left-hand side, this is a force term. These are all force terms, which have the units of newtons, for example. And these Q infinity S terms have the same units, force units. That means these aerodynamic coefficients should have no unit themselves. So you have force equal to force. If you multiply with something else, it will not be force anymore. So these have to be unitless. Okay, so you can write these aerodynamic coefficients as using these relations. So the lift coefficient is, for example, the actual lift force divided by Q infinity S term. So force divided by force, this is unitless. And again, these other force aerodynamic coefficients, they are all dimensionless numbers. Okay, so I'm not going to go into details of these aerodynamic coefficients. I will do that next week. So this is another area. Previously, I told you that aerodynamics people love working with non-dimensional numbers. So this is one of them. And as you will see next week, it is really tremendously beneficial to have these as non-dimensional numbers. But I will wait until Tuesday before I start talking about that. Okay? Any questions? Okay, so as I said, I should really start putting all this stuff on the web, because if we make the exam on the 22nd, then you should really have these terms. So I will try to do it over the weekend, but if I don't, please remind me that, okay? Sometimes I work with other things and these just slips my mind. Just either send me an email or post a message on Meteo Online asking for these materials, so I will put them. Okay, so I will see you on Tuesday. Ya öyle diye şey yaptık. O mantıklı görünüyor. Ne için?